Morning, my dear students. Welcome to Unacademy, welcome to Kreatryx channel, and welcome to Impulse batch. Before going to start today's session, let me introduce myself. I'm Swamy. I did my MTech in Systems and Signal Processing from JNT College of Engineering, Hyderabad. I have 12 plus years of teaching experience, and currently I'm associated with Unacademy. And if you want to purchase any course on Unacademy, you can use my code KVS Live, with which you will be getting flat 10% discount. Any course on Unacademy you can purchase using the code KVS Live. First of all, we'll observe what are the various courses for GATE we are having in Unacademy. Basically, we are having two types of subscriptions, namely the Plus subscription and the Iconic subscription. In the Plus subscription, the student will be exposed to live classes, crash courses, weekly tests, doubt solving sessions, and batches are conducted in both English and Hindi. If a student is not comfortable with English, he can take the batch in Hindi, and if a student is not comfortable with Hindi, he can take the batches in English from his choice of educator. And we have rank improvement batches as well. Coming to Iconic subscription, a personal coach is allotted to every student who will prepare the study planner. Study booster sessions are there. Separate test analysis is taken for each and every student. Dedicated doubt clearing instructors are there, and preparatory study material is also given to the students. If you examine the fee structure in Plus subscription, GATE or ESE preparation for 12 months, that is 1 year, it costs around 27,225 rupees only after applying the code KVS Live. In Plus subscription, GATE or ESE preparation, suppose if you are planning for 18 months, that is 1.5 year program, it costs around 34,650 rupees only after applying the code KVS Live. In Plus subscription, GATE or ESE preparation for 24 months, that is 2-year program, it costs around 39,600 rupees only after applying the code KVS Live. Coming to Iconic subscription, if you want to take your subscription in Iconic, so GATE or ESE preparation for 12 months, that is 1-year program, it costs around 45,225 rupees only after applying the code KVS Live. Iconic subscription, GATE or ESE preparation for 24 months, that is 2-year program, which is ideal for second year students. This costs around 66,600 rupees only after applying the code KVS Live. So you can have your choice either whether to go for Plus subscription or Iconic subscription, but don't forget to use the code KVS Live. And let me tell you that every week Unacademy is conducting an online exam known as Unacademy Combat, and this is going to happen this Sunday also, that is on May 23rd at 11 AM. And the branches eligible for this exam are mechanical, civil, electrical, electronics and communication, computer science and IT. What is the advantage with this exam? If your rank is in between 1 to 3, you will be getting 100% discount on Plus subscription, means you need not pay anything for Plus subscription. And if your rank is in between 4 to 10, 75% discount you are going to get. If your rank is in between 11 to 50, 50% discount you are going to get. And if your rank is in between 51 to 100, 25% discount you are going to get. And this is about this combat, which is going to happen on 23rd of May. And these are the batches which are there for ECE. For HAL, we have booster batch. For RSEB, we have booster batch for RSEB, booster batch for UPRVUNL, and booster batch for DFCCIL. And you need not pay anything for these batches. Simply take the subscription and you can attend any batch. And coming to the new batches of GATE and electrical, see, Ascent batch is there for GATE 2020, the aspirants of GATE 2023 electrical Ascent batch. So Evolve batch, GATE 2022 electrical, Ascent batch for 2023 ECE, and Evolve batch for 2022 ECE. So the batches have started on May 12th only. So you can take your subscription today also, no problem. And this is about an important information known as Navigate. See, this week Unacademy Combat is going to happen in the form of Navigate. See here, if you are going to write this combat exam, see there are lots of prizes to be won. So inform your friends also. So around 5 crore worth scholarships are there, and in order to write this navigate KBS live, you can use my code. So May 23rd, 11 a.m. 11 a.m. So Unacademy Combat is going to happen in the form of navigate this week. And this is regarding the practice series. Unacademy is conducting a Master Blaster practice series, a free special class series. Okay, so this will happen in the form of a special class. You can attend and you can use my code KBS live. And inform your friends as well. If you have any computer science friend, electrical, electronics, mechanical, civil, chemical, you please inform all of your friends. Okay, now it's time to get back to our discussion. So those who are coming, please give your attendance by pressing the like button. Good morning, Kaushik, Harish, Vinay, Venice. See, yesterday we had a problem with the YouTube, so that our topic got stuck in the middle. So today anyway we are going to continue the topic. Yesterday, if you remember, we have solved only two problems. Two problems we have solved. After that, look here, the important discussion is, listen carefully, how to extract the original signal from sample signal is the question. From sample signal. Actually, yesterday we were discussing this. Listen carefully. And I told you that this is available in many of the textbooks, but it is somewhat difficult to understand. How to extract the original signal from the sample signal. Share the session, my dear friends. Share the session. Now, if you want to extract your original signal from the sample signal, first of all, you must know what we have done in sampling. What we have done in sampling. The story of sampling in a nutshell can be shown like this. First of all, I took a signal x of t. I took a signal x of t which is band limited. Some x of t signal I took. Band limited signal. Band limited means what? Limited in frequency. How to band limit a signal? Pass it through a low pass filter. High frequency components will be automatically eliminated, so that this x of t forms a Fourier transform pair with x of omega. After band limiting, the spectrum of the signal can be shown like this. The spectrum of the signal is shown like this. This is x of omega. Now we band limited the signal by removing the high frequency components. After that, what we did in the story of sampling, see, we multiplied the signal with impulse train. No, if you want to sample in time domain, what we will do? Simply multiply with impulse train. How does an impulse train look like? Impulse train in time domain will look like this. So in order to sample a continuous time signal, we have to multiply with impulse train, right? Now impulse train, in see, whenever I am considering x of t, I am considering x of omega. Means if I am considering the impulse train, I must calculate the Fourier transform of impulse train, and we have seen that in while discussing the Fourier transform of periodic signals, Fourier transform of impulse train is again impulse train. So if you are going to take impulse train in time domain, its frequency domain also will get impulse train only. Here 2 pi by Ts will come, which is nothing but omega s, 4 pi by Ts, minus 2 pi by Ts, and so on. This will become 2 pi by Ts. So Fourier transform of impulse train is again impulse train. Now in time domain what we did, we multiplied in time domain. So in frequency domain, according to frequency convolution property, you have to convolve, no? Because the frequency convolution property says that if you multiply two signals in time domain, the equivalent operation in frequency domain is convolution. x1 of omega convolved with x2 of omega, right? Now if you multiply in time domain, the resulting sample signal will look like this, no? So how it will look like? The impulses, these impulses will take the shape of the time domain signal. Or we have one principle, no? Whenever you multiply any impulse signal with the signal x of t, will get the same impulse signal with area changed. So our area of the strength of each impulse will change like this. So this is the sample signal if I multiply. And what are the equivalent effect in frequency domain? And we know that if you sample the signal in time domain, see what is the equivalent operation in frequency domain? Convolution will happen, no? Convolution. So the spectrum or Fourier transform of sample signal, how it will look like? Suppose if I take the distance between adjacent samples to be in the time domain, if I take the distance between adjacent samples to be 1 by 2 fm, or if I select my sampling frequency to be omega s is equal to 2 omega m, omega s is equal to 2 omega m, which corresponds to critical sampling. Now what will happen? Observe, in frequency domain convolution will happen. Convolution, look here, x of omega, this is impulse at omega is equal to 0, means again I will get x of omega, but weighted by 1 by ts. This x of omega convolved with del of omega minus omega s. So this kind of periodical repetition I am going to get. This kind of periodical repetition we are going to get. This we call by the name sample spectrum. What is the name we gave for this one? Sample spectrum. And we have seen the story till here. Right? Now from the sample spectrum, now the question arises is that from the sample spectrum, how you are going to get your message original signal back? How you are going to get your original signal back? This is the spectrum I got now. See, in time domain, this is my sample signal. In frequency domain, it will look like this. Sample signal, Fourier transform is periodical repetition. From this periodical repetition, how I am going to get the original signal back? And we have seen that array pass it through a low pass filter. Now that can be shown like this. Observe here, lot of important things are going to come. See, low pass filter. Now sample spectrum in frequency domain, look here. In frequency domain, how the sample signal will look like? Minus omega m to omega, periodical repetition. Remember, 1 by ts, this is x sample of omega. For the case of critical sampling, God band is absent. This kind of periodical repetition is going to come. Listen carefully, my dear students. Hope you are not having any doubt up to this point. Now, I want to reconstruct my original signal. Reconstruction means what? Again, if I pass it through a low pass filter, I must get this Fourier transform back. This Fourier transform. If I can get this x of omega back, so if I take the inverse Fourier transform, again I'll get x of t. No? So how to get our original spectrum? How to get the original Fourier transform? Do one thing. You pass this through a low pass filter. Low pass filter. The low pass filter characteristics can be shown like this. Low pass filter. So this is the frequency response of low pass filter. Frequency response, what does it tell? Frequency response tells us the filtering capability. Means if I pass this periodical repetition through this low pass filter, so the low pass filter will pass only the frequency components that are lying in the pass band range. Pass band range is this one. Now here I'll take this to be minus omega s by 2 to omega s by 2. Array, what is omega s? Omega s is nothing but 2 omega m na. We sampled it, I am assuming critical sampling. Omega s by 2 means, look here, omega s is equal to to omega m I took. Omega s by 2 means what? Omega m. So minus omega m to omega m. So whatever the frequency components that are lying in the range of minus omega m to omega m are passed and rest are rejected. Now what is that? What is that is present between minus omega m to omega m? This component, no? So this component only will pass and I am able to reconstruct my original signal back like this. This is in frequency domain. But my dear students, I have a question for you. Can anybody tell me what could be the gain of this low pass filter? Here low pass filter shape I have given, but here what should be the gain? It could be 1 or something. Can anybody give you a reply in the live chat? What could be the gain of this low pass filter I am using here? What could be the gain of the low pass filter? It is a previous gate question, my dear students. Here what could be the gain of the low pass filter? It is not 1 Vamsi, it is TS. Let me tell you, it is TS. Why it is TS? Because look here, before, see, this is my x of t, this is x of omega. So what is the amplitude? What is the amplitude of my x of omega at 0? 1. Means after reconstruction also I must get this one, no. But during sampling what happened? See, our periodical spectrum got multiplied by 1 by Ts. So I must cancel that 1 by Ts. So in frequency domain anyway multiplication will happen, no. So if this is Ts, again I am going to get 1 here. So remember, the gain of the low pass filter is also important. It is Ts. It was a previous gate question, let me tell you. Yes, Josna, you are right. Good, Josna. So this is, now I am going to reconstruct my original signal, but this is in frequency domain. Look here, this is in frequency domain, and already we have seen frequency domain means Fourier transform. See, can we see the same thing in time domain? Can we observe the same thing in time domain? If you are going to observe the same thing in time domain, lot of information is going to come. See, this is in frequency domain. Frequency domain is what? One way of analyzing, the other way of analyzing the signal in time domain. Sometimes time domain analysis is difficult, so that we go for frequency domain. Observe how much easier. Pass this periodical repetition through a low pass filter. So the frequency response, this is a pass band of the low pass filter. So what are the signal is there between minus omega m to omega, that will come. How much easier it is. But can you analyze the same thing in time domain? Yes, we must analyze. For competitive exam point of view, we must analyze. Now how you are going to analyze? Here multiplication is done in frequency domain, means what is the equivalent operation in time domain? Convolution, right? Now let's observe. Now in time domain what will happen? First of all, look here. See, in frequency domain I am taking frequency response. In time domain, what is the equivalent of frequency response in time domain? Or impulse response, because impulse response and frequency response, they form a Fourier transform pair. We know. Now what could be the impulse response? What could be the impulse response of this low pass filter? Can anybody tell me what is the impulse response? See, this is frequency response. What could be the impulse response? What could be the impulse response? Observe here. I'll tell you, don't worry. Look here. What is the, already we have seen while discussing duality property, what is the Fourier transform of sync T? Rectangular pulse varying from, exactly Josna, you are right. What is the Fourier transform of sync T? Rectangular pulse varying from minus pi to pi, isn't it? Right? Now if I calculate sync of T by Ts, how to get? Use scaling property. If this is my x of t, this is my x of omega. So this is x of t by Ts. Identify the scaling factor. Wherever you have omega, replace with omega by a, no? So Ts into omega Ts. So observe here. So how to get x of omega Ts? In x of omega, divide each point on the horizontal axis with what? Ts. So pi by Ts. minus pi by ts, and this becomes ts. Now pi by ts is nothing but what? See, omega s by 2, no? Omega s by 2 means what? 2 pi by ts. So omega here, omega s by 2 means what? Pi by ts only. So what is the impulse response? Sync pulse. Sync of t by ts. Sync of t by ts. Remember, sync of t by ts, this analysis. So what is the impulse response? Sync of, some patience is required, t by ts, right? So equivalent of frequency response, that is impulse response I got. Now what is the equivalent of sample spectrum? What is the equivalent of sample spectrum? Sample signal. Or what is the equivalent of sample spectrum? Sample signal. And how it will look like? This one only, right? So let me draw that. Equivalent of sample spectrum is sample signal, because whenever you are going to some textbooks, you will, I mean, this will be there, but you won't find very difficult to understand, but required for exam. This is example of t. Now can you give the time domain representation for example of t? Yes, I can give. Already we have seen while discussing sampling, we have seen what is the time domain representation. Summation n varying from minus infinite to infinite x of nts into del of t minus nts, or area of each impulse will change according to the signal, right? Now in time domain, how you are going to analyze and how you are going to get the shape. See, lot of information is going to come. Please be patient. Here I have impulse response, I have input and impulse response. We know that from the concept of LTI system, given input and impulse response, what is the output? Convolution. See, in frequency domain, we'll say that we'll pass it through a low pass filter, we'll get the original signal back. But in time domain, how that is going to happen? How we are going to reconstruct your original signal? You must observe, right? This is example of the convolve with h of t. Now convolve, input is there, impulse response is there. So output is summation. After the class also you must verify, my dear students. This convolved with sync of t by ts. Impulse response, no? Frequency domain multiplication, time domain convolution. Now what is the output here? Y of t can be written like this, summation n varying from minus infinite to infinite. X of nts is a constant value. Now what is the convolution of a signal with a shifted impulse? Shifted signal from the concept of LTI system. Sync of t minus nts by ts. Right? This is very useful in your communication also. Now we have to draw the signal y of t. First of all, try to understand what is y of t. Y of t is nothing but, see, summation n varying from minus infinite to infinite x of nts, sync of t minus nts by ts. If you are substituting different values of n, I'll get different sync functions weighted by x of nts. Now we'll observe how that is going to look like. So for that, I am removing this part. Okay. So what is my y of t? Now you will see how the signal is reconstructed in time domain. How much pain is there in time domain? This is what we got. Now what happens if I substitute n is equal to 0? Or whenever you have summation, what we'll do? We'll substitute different values of n. We'll substitute different values of n. What happens if I substitute n is equal to 0? N is equal to 0 means x of 0 weighted by sync of t by ts. Sync of t by ts, look here my dear friends, it will look like this. Sync of t by ts. So this will be 0, this will be ts, this will be 2ts, this will be minus ts, this will be minus 2ts. After the class you can verify all this. Now this is what is your signal shape for if I substitute n is equal to 0, sinc of t by ts weighted by x of 0. X of 0 means here this is this value. Now what happens if I substitute n is equal to 1? What happens if I substitute n is equal to 1? Sinc of t minus ts by ts. Sinc of t minus ts by ts is nothing but shifted version of sinc of t by ts by 1 unit, sorry, by ts weighted by x of ts. X of ts means this value weighted by x of ts. So its shape will be like this. Shifted sinc functions you are going to get. Shifted sinc functions. It is going to come like this. This is for, let me write here, this is for n is equal to 0. This is for n is equal to 1. And what happens if I substitute n is equal to, what happens if I substitute n is equal to minus 1? X of t plus ts by ts means sinc of t by ts is advanced, means shifted to the left by ts, and its shape can be shown like this. This is for n is equal to minus 1. Now, and so on. See, I cannot draw every sinc pulse here, and so on. You can put dots. And if you are going to add all the sinc pulses, remember my dear students, if you are going to add all the sinc pulses, you are going to get the shape of the original signal. All the sinc pulses addition will give the shape of the original signal. See, what is the original signal shape? This one, this original signal shape. See, x of t, this will be reconstructed. This much is there in like this. Original signal can be reconstructed. So this is how we are going to observe in time domain, right? And remember, look here, remember here what I am doing. I am in frequency domain, I am taking a low pass filter. In frequency domain, I am taking a low pass filter, and its time domain impulse response is sinc pulse. So as we are going to take a low pass filter, now if you observe, low pass filter is limited in band, so it is also known as band limited interpolation. So this way of passing your signal through a low pass filter to get your original signal back is what is known as band limited interpolation. This process, band limited interpolation. Remember, if anybody asks you what is band limited interpolation, means after sampling we'll pass the sampled signal through a low pass filter. As low pass filter is limited in band, means limited in frequency, it is known as band limited interpolation. And as we are going to have sinc pulse in time domain, it is also known as sinc interpolation. Both are same. Band limited interpolation or sinc interpolation are same. Band limited interpolation or sinc interpolation are same. गजेंद्र सिंह, सिग्नल अलावा कौन से सब्जेक्ट आप लेते हो? मैं कम्युनिकेशन लेता हूँ यार गजेंद्र. So band limited interpolation or sinc interpolation. Right? This is how we are going to analyze in time domain. After the class, you try to examine, or if you have any, if you know any tools, try to see whether you are going to get the original signal or not. So this much pain is there in time domain. Remember, in time domain, sinc pulse is there, no sinc interpolation. So frequency domain, low pass filter. Low pass filter is limited in band, means it is limited up to a only certain band in frequency domain. It is also a band limited interpolation. Both are same. See, apart from this sinc interpolation, we have other interpolating functions also. They are, look here, if the impulse response, see the impulse response of the filter can be like this also. a rectangular pulse. See, already we have seen this one. See, based on the requirement, you can have different interpolating function, means impulse response can be of this shape also. So, if you are going to have this kind of impulse response, that is if your impulse response is of rectangular pulse shape, it is known as step interpolation. Step interpolation. Step interpolation. Step interpolation means your impulse response is taking the shape of a rectangular pulse. So, already we have seen this one. This is known as sync interpolation. Impulse response is taking the shape of sync pulse. Sync interpolation. Sync interpolation. See, impulse response can take this shape also, a triangular pulse shape. This is known as linear interpolation. Linear interpolation. Linear interpolation. Linear interpolation. Apart from the step interpolation, sync interpolation, linear interpolation, we have one more type of interpolation known as raised cosine interpolation. Raised cosine interpolation. Whose impulse response can be given like this. It is a modification. Remember, raised cosine interpolation is a modification to sync interpolation. Just I am going to give the impulse response. I am not going to discuss anything about this. H of t is equal to, this is sync interpolation. Sync interpolation is multiplied with those who have studied communication. In communication, we have intersymbol interference. Same concept will come there also. Raised cosine pulse we are going to have there. This is the impulse response of raised cosine interpolation. Just take down this information, and here R is known as roll-off factor. See, if you are going to reconstruct your original signal using sync pulse and raised cosine pulse, the performance of raised cosine pulse is better compared to sync pulse due to the multiplication with this factor. How this factor came and what happens if I multiply this factor, what is the equivalent effect in frequency domain, all that will come in communication. Intersymbol interference is not a discussion of this part. And remember, the roll-off factor will lie between 0 and 1. 0 and 1. And if R roll-off factor is 0, so your raised cosine interpolation, see this, it will become sync interpolation only. Okay, fine. The idea of the discussion is how to reconstruct the signal in time domain. Frequency domain, anyway we know that low pass filter rectangular pulse shape, we are going to take in frequency domain and pass the spectrum. In time domain, you can use either this kind of rectangular pulse, sync pulse, or triangular pulse, or raised cosine pulse. Okay. The next topic, what I am going to discuss now is, it is also an important topic, range of frequencies of low pass filter, because low pass filter is used for reconstruction, no? For signal reconstruction. Range of low pass frequencies of low pass filter for signal reconstruction. Again, we can show like this. We started with a band limited signal. Okay, we took a band limited signal. Now we sampled. What happens if you are going to sample? If you sample a signal in time domain, periodical repetition is going to occur in frequency domain given by this expression. Sample spectrum. This you have to remember, very very important. Now how to draw the sample spectrum? Give different values of n. What happens if I substitute n is equal to 0? I will get the original spectrum, which is from minus omega m to omega m, weighted by 1 by Ts. What happens if I substitute n is equal to 1? X of omega minus omega s. I am considering oversampling. I am considering oversampling. Oversampling means what? Omega s greater than 2 omega m. Always remember, my dear students, in practice we will go for oversampling only. We won't be going for critical sampling. See, if you are going for critical sampling, the design of low pass filter will become very difficult. The design of the low pass filter will become very difficult, because for critical sampling you need a sharp cutoff low pass filter. Sharp cutoff low pass filter means like this. This is the pass band, this is the stop band. So here there must be a sudden transition from pass band to stop band. Look here, this is an ideal filter. There must be a sudden transition from pass band to stop band when we are going to use an ideal filter, but these kind of filters cannot be realized in practice. Such sudden transitions from pass band to stop band cannot be achieved practically. Why we are not going to achieve? Let's observe within 10 to 15 minutes. In the next topic I am going to explain. So here always oversampling is only preferred. Now what happens if I substitute n is equal to minus 1? This kind of periodical repetition we are going to get. Already we have seen this. This is my example of omega. From this periodical repetition, we can get our message signal back by, original signal back by passing through a low pass filter. Look at this green line, green dotted line indicates the low pass filter characteristics, where the cutoff frequency, this is omega s plus omega m, this is omega s minus omega m, where the cutoff frequency omega c of the low pass filter must lie between, see, this is practical filter, this is ideal filter. Ideal filter, practical filter will not have sudden transitions, but they will have gradual transitions from pass band to stop band. So where the cutoff frequency of the low pass filter must lie between, what is the range? Omega c must lie between omega m and omega s minus omega m. Based on this relation also previous gate questions were framed. Remember, my dear students, based on this relation also previous gate questions were framed. Cutoff frequency must lie between, for a practical filter, omega m and omega s minus omega m. Now here also, from here also you can identify. I told you, see, this is low pass filter, no? So what could be the gain of the low pass filter? Again, I must, if I reconstruct, I must get 1, means, see, whenever I sample, the sample spectrum is weighted by Ts, means the gain of the low pass filter must be Ts, so that Ts and 1 by Ts gets cancelled. We'll do one thing, we'll try to solve one previous gate question based on this, so that we'll get confidence. Let's solve one recent previous gate question, that is a band limited. Try to understand each and every term. Band limited means limited in frequency. Low pass signal means Fourier transform centered around 0 of x of t of bandwidth. Bandwidth means highest frequency minus lowest frequency for positive frequencies, 5 kilohertz, is sampled at a sampling rate fs, is sampling at a sampling rate fs. Now after sampling, what is doing? The signal, you want to reconstruct, the signal x of t is reconstructed. Reconstruction means he must pass the signal through some filter. The signal x of t is reconstructed using the reconstruction filter. Using the reconstruction filter, he said. Reconstruction filter with frequency response. Yes, in frequency domain, with frequency response h of f as shown. Means he is giving the frequency response, right? Whose magnitude of the frequency response you take? Magnitude of frequency response is shown. From this he is asking the minimum sampling rate Fs in kilohertz for perfect reconstruction. Perfect reconstruction of x of t is. The filter characteristics are shown like this. Magnitude of the filter characteristics are shown like this. We have seen now in practice we are not going to have ideal filters, practical filters. 6, 8, -6, -8. Come on, try to solve this problem. F is given in kilohertz. This is some K. Come on, tell me what is the value of good morning, Naman. Tell me what is the value of Fs. What is the value of Fs? Try to read the problem. Whenever you are given a problem, forget the answer. Try to read the problem, what the information you are going to have. Recently, 1 or 2 years back, I think this problem was given. I didn't remember the year, but this is a previous gate question. Josna, actually it is given under numerically based, means you cannot use greater than 13 or something. It must be a value. You cannot use the operators there. It is a value. Any answer? Okay, let me try this one. Meanwhile, if you are getting any answers, type your answers in the live chat. It's a very simple question, nothing before you. Right. Now, according to the information what he gave, there is a signal x of t, band limited signal x of t. This kind of shape I am taking, band limited. Now, -5 kilohertz to 5 kilohertz. Right. So, this is x of f. X of f. This is before sampling. This is before sampling. What he did, he sampled this signal. So, in frequency domain, what you are going to get? You are going to get periodical repetitions. So, x sampled of omega is 1 by Ts summation n varying from -infinite to infinite. Periodical repetition will come omega minus n omega s. X sampled of f. Suppose if you are going in f domain, so 1 by Ts, this will come. X of f minus n fs will come in f domain. Now, how the spectrum will look like? n is equal to 0, the original spectrum will come. N is equal to 0, the original spectrum will come minus 5k to 5k. What happens if I substitute n is equal to 1? X of f minus fs means centered around fs. This is a, what will happen? You can observe, just now we have seen, no, omega s minus omega m, omega s plus omega m means fs minus fm means fs minus 5k. This must be fs plus 5k. Any answers, or nobody is giving answers? What happened, yaar? Now this kind of periodical repetition is going to come, minus fs. Now he is passing this one through a filter like this, some filter. Now in order for perfect reconstruction, here what is this value? This one is 8, this is one is 8k, this one is minus 8k. For the perfect reconstruction means what? If you pass the signal through this kind of filter, only our original signal must come. No other component of the periodical repetition will not must come, isn't it? If I pass, look here, if I pass our original periodical spectrum to this kind of filter, only our original spectrum must absorb at the output. Means, look here, output must be again this one. Output must be again this one. And this will happen if, can I say that if fs minus 5k, look at fs minus 5 kilohertz must be greater than or equal to 8 kilohertz. Yes or no? This limit fs minus 5k must be greater than this limit, greater than or equal to this limit. Otherwise, otherwise what will happen? Some portion of the some portion of this spectrum will also come at the output. So in order to avoid that, fs minus 5k must be greater than or equal to 8k, or fs must be greater than or equal to 13 kilohertz. Our minimum value is what? 13 kilohertz. Minimum value is 13 kilohertz. In order for the perfect reconstruction, what is the condition? This limit fs minus 5k must be greater than or equal to 8k. This, see, the lower limit of the Fourier transform centered around fs must be greater than or equal to 8k. Clear? Please reply so that I can move forward. Please reply. If you understand, reply with a thumbs up. Simple problem. Now you can have analysis also. You do one thing. Fs is equal to 13k you take, Fs is equal to 12k you take, Fs is equal to 11k you take, and see whether you are going to reconstruct or not. You can extend also. You can extend this problem. Take Fs is equal to 13k. See, let me solve that one. Look here. Always try to analyze the problem in different ways. Now this is minus 5k to 5k, my original signal. Now what happens if I sample this one at fs is equal to 13k? So the periodical spectrum will come like this, minus 5k to 5k. Now after that, centered around 13k, 13k minus 5k, 13k minus 5k, 8k, 13k, 18k. This kind of spectrum I am going to get if I take fs is equal to 13k. And what is our filter? Our filter is like this, no? Is like this. Yes, perfect reconstruction. no portion of the other signal is coming. It's a perfect reconstruction is happening. What happens if I take Fs is equal to 12k? You must analyze whenever you are studying, you must analyze like this. Fs is equal to 12k if I take, what will happen? Minus 5k to 5k you are going to get. So centered around Fs means 12k. 12k plus, look here, 12k plus 5k, 17k, 12k minus 5k, 7k. Similarly here also. Now when I pass this through this kind of filter, our filter is like this. Its pass band is from some minus 8k to 8k. Here if you observe, perfect reconstruction is not possible because this component is also coming. This component which is unwanted is also coming. So Fs is equal to 13k. After that you can take 14k, 15k, anything. Understood? In this way you have to analyze. See, whenever you are solving the problem, if you are going to get the answer, try to analyze, do some reverse engineering also, so that your concept becomes stronger. Or Fs is equal to 13k I got, but let's analyze. What happens if I take Fs is equal from the expression I got? See, what happens if I take Fs is equal to 12k? This kind of situation will come if I take Fs is equal to 12k. Right, completed. So this is all about the sampling. Only some portion of the sampling is completed. As far as sampling is concerned, only some portion means the common portion related to electrical and ECE and instrumentation is completed, but sampling topic has more features. See, what are the sampling we have seen is for low pass signals. Signals of this kind are known as low pass signals, whose Fourier transform is centered around 0. But what is the Fourier transform of band pass, what is the sampling, how we are going to sample a band pass signal, that we haven't seen. And this is nothing but the sampling technique. What we have seen is ideal sampling or theoretical form of sampling, where we multiply the signal with impulse train. We'll study in the first basic units that impulse signal cannot exist in practice. Look here, ideally impulse signal cannot exist in practice. If impulse signal cannot exist in practice, there is no question of impulse train, right? So what are the sampling technique we have seen is ideal form of sampling, because in practice impulse signal will not exist. Then what is the question of impulse train? So the method what we have seen is ideal form of sampling or theoretical form of sampling. But how sampling is going to happen practically means there are two approaches, natural sampling and flat top sampling. Those are part of EC syllabus but not for electrical students. So as this batch is for common for EC and electrical and instrumentation, I am not going to discuss those topics now, but definitely I will discuss after some time. After electrical syllabus is completed, I am going to discuss what is the proof for band pass sampling of band pass signals and natural sampling, flat top sampling, what are the various problems in flat top sampling like aperture effect and how to avoid that aperture effect. All those topics we will discuss later. As far as common portion is completed, okay, fine. This is what is your sampling. How to find out the Nyquist rate, Nyquist interval, and what are the low pass filter characteristics and how you are going to reconstruct. This much knowledge is sufficient. Low pass signals, band pass signals, and practical approaches of sampling like natural sampling, flat top sampling, we will discuss later. Okay, so this is about sampling. This is an application of Fourier transform. Now let me take one more application of Fourier transform, that is distortionless transmission. Hope everybody is confident with sampling. Give a thumbs up so that I can know from response from your side. Okay. See, distortionless transmission. What is the concept of distortionless transmission? Suppose if I am having an LTI system. LTI system with frequency response h of omega. So what is frequency response? Fourier transform of impulse response is frequency response. Now if I am going to give at the input a signal of this kind, x of t, x of t. Now at the output I may expect this kind of signal or this kind of signal. Now if you observe the first output, there is no resemblance with the input. If you observe the first output, there is no resemblance with the input signal, or we can say that the first output is distorted version of the input signal. Distorted means shape is disturbed, right? And if you observe the second output, shape is preserved, but there is some delay. And remember, always delay is allowed, delay is not a problem. And if you observe, amplitude scaling is also done here, and amplitude scaling is also allowed, but shape must be preserved. Or can I say that the second output, what I am going to get here is undistorted version of the input signal, Now if the second one is the undistorted version of the input signal, what I am taking here, can I give the input output relationship? Can I give the input output relationship of a distortionless transmission like this? Y of t is equal to k into x of t minus t naught, where we have delay and amplitude scaling, both are allowed. Delay is allowed, amplitude scaling both are allowed. This is the input output relationship of a distortionless transmission. Delay is allowed, amplitude scaling both are allowed because they won't affect the signal shape. Now we have to determine under what conditions, look here, under what conditions our LTI system will produce this kind of undistorted output, or what are the conditions on the frequency response so that we are going to get this kind of undistorted output, we must observe. For that, do one thing, simply calculate the Fourier transform on both sides. Y of omega is equal to, use your shifting property, e power minus j omega t naught multiplied with x of omega. Now you calculate y of omega by x of omega. Y of omega by x of omega is your h of omega frequency response, k e power minus j omega t naught, or h of omega is k e power minus j omega t naught. This is the frequency response. And remember, in practice always we are going to apply real signals only. So for real signals, Fourier transform can be written like this. It will have magnitude and it will have phase, right? The frequency response will have magnitude and phase. Now what is magnitude of h of omega if you compare? K, phase of h of omega is minus t naught into omega. Now if you try to plot the free magnitude and phase, see, magnitude of h of omega is equal to k, means constant. In frequency domain it is a constant, right? Now how you are going to plot this one? See, this, if you observe, this is in the form of y is equal to minus mx, isn't it? Sorry, y is equal to mx y is equal to mx, where the slope is minus t naught. Now, what is the shape? If you try to plot the phase of h of omega versus omega, so y is equal to minus mx will look like this, right? Here, what is the slope? Slope is minus t naught. Slope is minus t naught. So, if your frequency response, magnitude response and phase response are like this, definitely you are going to get distortionless transmission. So, what are the conditions for distortionless transmission? Conditions are important. In exam, in gate exam, they always ask the conditions. Magnitude of the frequency response must be constant. Observe here. Magnitude of the frequency response must be constant and phase must be a linear function of frequency. Phase must be a linear function of frequency. So, you can summarize like this. For distortionless transmission, magnitude of frequency, or we'll make points like this. For distortionless transmission, magnitude of frequency response must be constant. Phase must be a linear function of frequency. Magnitude of frequency response must be, these are the conditions. Magnitude of frequency response must be constant and phase must be a linear function of frequency. Remember, if the magnitude is not constant over the frequency range, we are going to get magnitude distortion or amplitude distortion, and if the phase is not linear function of frequency, we are going to get phase distortion. Phase distortions will occur. You remember these two statements. Magnitude of the frequency response must be constant and phase must be a linear function of frequency. Phase must be a linear function of frequency. Okay. Completed? Now, in the previous discussions, I told you that why ideal filters cannot be realized in practice. We have seen, no? See, while discussing sampling, just before 10 minutes, I told you that we cannot have ideal filters in practice. Now, why ideal filters cannot be realized in practice? Suppose if anybody asks you, see, it is a general statement. We cannot realize any ideal low pass filter or band pass filter or band stop filter. Any type of ideal filters we cannot realize. But what is the reason behind that? So, the discussion is, listen carefully, my dear students, why ideal filters cannot be realized in practice. Somewhat patience is required to understand this topic. Why ideal filters cannot be realized in practice? Means why we cannot realize an ideal low pass filter or band pass filter or band stop filter. What is the reason? What is the reason? Very simple. Look here. Now forget about all kinds of filter. I am considering a low pass filter. Low pass filter. Now low pass filter means its frequency response can be shown like this. To understand in a simpler way, without any complicated expressions, okay. the frequency response of low pass filter can be shown like this, right? The frequency response of low pass filter. Now if you observe, this is the pass band, this is a pass band, this is a stop band, again this is a stop band. Pass band means what? See, the frequency components lying between the range of minus omega c to omega c are passed, rest are rejected. In the stop band, if any frequency lies in the stop band, it is not allowed. So the name stop band. Pass band means in this range, the frequency components lying in this range of minus omega c to omega c are passed. Pass band, stop band. Now if this is the frequency response, and I'm going to consider only the magnitude response here, I'm neglecting the phase for the sake of simplicity. I'm neglecting the phase. Can I say that, look here, this is pass band, this is pass band, this is a stop band. Can I say one important statement that in the pass band, transmission must be distortionless? Observe here, in the pass band of any filter, transmission must be distortionless. See, whenever we are going to pass the signal through a filter, we must get the exact shape. Means in the pass band, what conditions must be satisfied? Distortionless transmission conditions must be satisfied. So simply I can write like this: in the pass band, transmission must be distortionless. Transmission must be distortionless. Distortionless means in the pass band, magnitude of the frequency response must be constant and phase must be a linear function of frequency. But I am not going to include the phase because for the sake of simplicity, you can include the phase also. In the pass band, transmission must be distortionless. Observe here, it is satisfied. Magnitude of the frequency response is constant, right? I am not including the phase. Now if this is the frequency response, can you tell me what is the impulse response? We have seen in the earlier discussions. We have seen see, frequency response is this one, means impulse response is a sync pulse. Frequency response of low pass filter is a sync pulse. Sorry, impulse response of a low pass filter is sync pulse. So impulse response, what could be the shape here? This is the impulse response. Agreed? Impulse response. Look here, this is the frequency response, this is the impulse response, right? Now if you observe this impulse response, does your h of t is 0 for t less than 0? Does your h of t is 0 for t less than 0? No, h of t is not equal to 0 for t less than 0. H of t not, impulse response is not 0 for t less than 0. Means from your concept of LTI systems, if impulse response is not equal to 0 for t less than 0, means what is the name you are going to give? Causal or non-causal? Causal or non-causal? If impulse response is not 0 for t less than 0, so it is a non-causal system. Non-causal system can you realize in practice? While discussing the second unit, I told you all physically realizable systems are causal systems. Non-causal systems we cannot realize. Non-causal systems we cannot realize. So why ideal filters cannot be realized in practice? If anybody asks you, you must reply it as ideal filters are non-causal. Ideal filters are non-causal because impulse response is not 0 for t less than 0. T less than 0. Simply you can remember like ideal filters. If anybody asks you why ideal filters cannot be realized in practice, because ideal filters are non-causal. See, one condition I am giving here for practical. For practical realization of any filter, two conditions must be satisfied. Two conditions. First one is your impulse response must be 0 for t less than 0, means it must be causal. This is what is known as the time domain condition. Time domain condition, impulse response must be 0 for t less than 0. In frequency domain also we can give the condition that your frequency response must satisfy this expression, ln of mod of h of omega by 1 plus omega square d omega must be less, just take the expression, must be less than infinite. This is what is known as Paley-Wiener criterion. Paley-Wiener criterion. See, in order to gain some knowledge on distortionless transmission, you can do one thing, refer Signals and Systems by B.P. Lathi textbook. B.P. Lathi. He has presented in a very good way. B.P. Lathi textbook. You will get all the, what I have used, all you will get there. B.P. Lathi is a very good book. So, time domain, it must be causal, h of t must be 0 for t less than 0, and in frequency domain, Paley-Wiener criterion must be satisfied. Ln of mod of h of omega by 1 plus omega square d omega must be less than infinite. If you want further information on the other types of filters and all, refer B.P. Lathi textbook. There you can find the entire information. Right. Now, after this, I am going to discuss two important terms known as phase delay and group delay. Phase delay and group delay. Questions are expected from this two expressions, phase delay and group delay. Phase delay and group delay. Now, how to understand this phase delay and group delay in a easier way? Observe here. Consider an LTI system like this with frequency response h of omega. Listen carefully, my dear students. Consider LTI system with frequency response h of omega. Now, I am going to give this kind of signal as the input, x of t cos omega ct. Now, whenever you are going to pass any signal through a LTI system, definitely delay is expected at the output. Delay is expected at the output. Now, before passing, let us analyze our signal x of t and cos omega ct. Now, can you tell me how many frequencies are there in x of t? Suppose if I take my signal like this, some ordinary signal I am taking like this. So, how many frequencies are there in the signal x of t and how many frequencies are there in cos omega ct? First of all, you must know this one. Remember, there are many frequencies, there are infinite number of frequencies are present in x of t. Suppose, look here, in time domain, remember my dear students, in time domain, if I am drawing a arbitrary signal like this, suppose if I say that this is my x of t, you see this x of t is formed by, look here, you must remember, you must observe like this, x of t signal is formed by adding different frequency components. By adding different frequency components, we are going to get the signal x of t. Now, if I will say rectangular pulse means what? This kind of shape we are going to have. How we are going to get rectangular pulse? By adding different signals of different frequencies, or by adding different sinusoids with different frequencies, we are going to get this kind of shape. Right? Now, if you observe in this x of t, there are low frequency component, there are high frequency component, many frequency components are there. How can you say? Calculate the Fourier transform. Fourier transform will give the frequency domain representation, no? Yes or no? Frequency domain representation. See, from the Fourier transform we can know that this is low frequency part. and these are high frequency contributions. So low frequency portion is predominant here, means with low frequency components I'll get the shape of this rectangular pulse, and by adding high frequency components the sharpness of the signal increases. Or we can say that there are infinite number of frequencies. How many frequencies are present in this rectangular pulse means infinite number of frequencies. How can you say, anybody ask you, how can you say, means, draw the Fourier transform. This Fourier transform is existing from what value to what value? Minus this omega is varying from what value to what value? Minus infinite to plus infinite, means that many frequency components are there in our signal x of t. Or simply can I say that our x of t is combination of group of frequencies. Many frequencies are there, right? Now in cos omega ct, how many frequencies are there? I can say that only single frequency. Again, if you say, the other person will ask, how can you say, draw the Fourier transform? Or Fourier transform is only the technique. So cos omega ct means what? One impulse at omega c, the other impulse at minus omega c. Only single frequency is present here. So single frequency. Whereas x of t, the other signal, see, it could be a rectangular pulse or any other pulse, it will have infinite number of frequencies. And if you are going to pass this kind of signal, x of t multiplied with cos omega ct. So whenever you are going to pass, there may be a delay in the signal x of t and there may be a delay in the signal cos omega ct also. So the delay what I am going to get here in the signal x of t is what is known as group delay, means group of frequencies, many frequency components are there. So here this delay is known as group delay, and whereas the delay what I am going to get here in the, this is omega cos omega ct, this is known as phase delay, group delay, phase delay. Phase delay means delay occurring at a single frequency. Group delay means delay occurring for a group of frequencies. Remember, this x of t can also be called as envelope. So those who are from ESE background, they can understand better. This is called envelope, and this is our carrier signal. So the delay which is going to come in the envelope is nothing but group delay, and the delay which is going to come in our carrier, which is nothing but phase delay. The delay coming for group of frequencies, group delay, the delay occurring at a single frequency, phase delay, that's it. Okay. The point here is, you must understand, if anybody asks you how many frequencies are there in this kind of signal, means you must say infinite number of frequencies are there, and they are in a equilibrium, because they are in equilibrium such that we are going to get this kind of shape. If you change the equilibrium or if you disturb the equilibrium, this shape will be disturbed. Suppose I am going to disturb the equilibrium, I am going to disturb the high frequency components, yes, shape will become like this. High frequency components are responsible for sharpness. If I remove the high frequency components, the pulse gets smoothened like this. Remember, this much concept is there. So group delay, phase delay. Now there are expressions for group delay and phase delay. If you remember those expressions, you can solve the problems. Phase delay, Tp of omega denoted by minus theta of omega by omega. That's it. Group delay, see, if you remember the condition for distortionless transmission and these two expressions, it is enough. Group delay minus d by d omega of theta of omega. And remember, for distortionless transmission, these two will be equal. For distortionless transmission, phase delay and group delay will be equal. For distortionless transmission, phase delay and group delay must be equal. How can you verify? I've given one statement. Whenever I'm giving something, means reverse engineering we must do after the class. You must have a doubt. See, always having a doubt is very good, because that will make you think. See, for distortionless transmission, phase delay and group delay, sir has told that phase delay and group delay must be are equal, he said. So how that is going to happen? Distortionless transmission means what? Magnitude response must be constant and phase must be a linear function of frequency. Acha, phase must be a linear function of frequency. Means for distortionless transmission, can I take this one? Okay. For a distortionless transmission, phase must be linear. Theta of omega is equal to omega means acha, this is in the form of y is equal to x. Linear relation. Phase is linear means this is the phase of a distortionless transmission. Okay. Let's substitute theta of omega is minus theta of omega by omega minus 1. Okay. Let's find out the group delay. Minus d by d omega of theta of omega. Yes, it is satisfied. Remember, for distortionless transmission, phase delay and group delay are equal. Okay. These concepts, distortionless transmission and the previous ones what we have seen, they are important for analyzing intersymbol interference in digital communication. Okay. Now let's solve some problems. I think from the morning we are discussing only problems. Let's solve 2 or 3 problems and we'll wind up the class. First question. The frequency response. Okay, whenever I write frequency response means one point must strike in your mind. Acha, Fourier transform of impulse response gives frequency response. Frequency response tells us the filtering capability, and based on frequency response only we are going to categorize filters as a low pass filter or high pass filter or band pass filter. So everything must come in your mind. So the frequency response of a LTI system is 1 minus j omega by 1 plus j omega. The group delay after this we'll solve one previous gate question. This is not a previous gate question. After this we'll solve. Come on, give your answers. Options are also I'm giving. Let me tell you, tomorrow, see actually I thought of starting Hilbert transform, but time is not sufficient. Tomorrow I'll be starting Hilbert transform. Hilbert transform is not there for electrical students basically, but if you are going for IS, the Hilbert transform is there. But I request every electrical student also attend the Hilbert transform, because this is just an application of Fourier transform and you will really enjoy Hilbert transform. Applications of LTI systems and Fourier transform we'll see. You will enjoy Hilbert transform. After that, I am going to start your favorite unit, Laplace transform. Vamsi Krishna has given answer D. Let me collect some more answers, Vamsi. Definitely you must attend. You will enjoy. Come on, I want the answer. One more problem is waiting for you. Previous gate question. For those who are attending the class, please give your reply. Josna Reddy C. See, first of all, what is the expression for group delay? It is minus d by d omega of theta of omega. Now get the phase and differentiate. What is theta of omega? How to get phase of the numerator minus phase of the denominator? Phase of the numerator minus tan inverse of omega minus phase of the denominator minus tan inverse minus 2 tan inverse of omega. Group delays minus d by d omega of theta of omega minus 2 tan inverse of omega. It is 2 by 1 plus omega square. Option C will become the right answer. Josna, you are right. Haresh, you must be very careful. Vamsi, minus symbol. Okay, let me give you one previous gate question. I'll see who will answer this one. The input to a channel means it can be considered as a low pass. See, the channel can be considered as a system. The channel may have low pass filter characteristics also. In communications, many times we'll consider the channel to be a low pass filter. Okay, the input to a channel is a band pass signal. Okay, it's a band pass signal, is it? Fine. Band pass signal means it is obtained by linearly modulating a sinusoidal carrier. Oh, fine. Carrier with a single tone. Single tone. Fine. Single tone. Tone means frequency. Single tone means single frequency signal. Means carrier. The output of the channel. Okay. Same concept what we are discussing. Due to input is some y of t is equal to 1 by 100 to cos of 100t minus 10 power minus 6 into cos of 10 power 6t minus 1.56. The group delay Tp and phase delay Tp. Are options also I am giving. Come on, you try to calculate, forget about the options. Come on, what is the answer? A, B, C, D. This is a previous gate question. Hint is, look here, hint, whatever I told here, in the same way the question was framed. The same way question was framed. See here, he is passing this signal through a channel, and in the signal what is passing, there is a single tone signal. See, single tone signal is there, means signal consisting of single frequency, and a carrier is also there. Okay, so he is asking us to get the group delay and phase delay. Or D. Let me try. What is y of t? Very simple. Y of t is 1 by 100 output e cos of 100t minus 10 power minus 6 cos of 10 power 6t minus 1.56. Right. Now here always remember the delay which is occurring in the message signal, delay occurring in the message signal is phase delay, delay occurring in the carrier is group delay. Delay in message, phase delay. Delay in carrier, group delay. See, message signal may consist of single frequency or many frequencies. So the delay occurring in message is phase delay, carrier is group delay. Now how to identify? Those who are studying new for the first time, you may have a doubt regarding this problem. How to identify which is carrier and which is message? And always remember, carrier frequency, if FC is the carrier frequency, it must be very much greater than the message signal frequency. Carrier frequency is always more. Carrier frequency is always more than the message signal. Those are from electrical background, you can understand like this. Carrier frequency is always greater than the message signal frequency. Now here what is the carrier and what is the message signal? So carrier, see what is the frequency here? 10 power 6, 1 megahertz. Here 0.1 kilohertz. So this is the carrier. Okay, fine. How I identify this as carrier? Carrier will have more frequency. So this is the message signal or baseband signal we'll call. You can call it as information carrying signal. Many terms are there. Message. So delay occurring in message is phase delay. Delay occurring in carrier is group delay. Now can I modify my y of t like this? 1 by 100 cos of, take 100 common, 10 power minus 8 10 power 6 you take common, yes. So that now what is the delay here? What is the delay? So this is message signal. So the delay is nothing but phase delay. Sorry, delay in the message signal, phase delay. What is the delay? I think I have written wrong here. Delay in the message is group delay. Sorry. Delay in the message is group delay. Delay in the carrier is phase delay. Delay in the message is group delay. Delay in carrier is phase delay. Now this one is your message signal, group delay. So I'll get group delay here. What is your group delay? 10 power minus 8 seconds. And what is your phase delay? 1.56 into 10 power minus 6. Now choose which option will match. Group delay is 10 power minus 8, phase delay is 1.56 into 10 power minus 6. Option B will become the answer. Just already not option A, it is option B, because delay in message is group delay, delay in carrier is phase delay. Hope this is clear. Generally message signal will have so many frequencies, no? So group delay, carrier means single frequency, phase delay. Now before leaving, let's solve a small problem, previous gate question, very simple question. You can easily answer. GATE 2002 it was given. A linear phase channel with phase delay TP and group delay TG must have a TP is equal to TG is equal to constant, TP proportional to F, TG proportional to F, TP is equal to constant, TG proportional to F, TP proportional to F, TG is equal to constant. Come on, what is the answer? Simple question. The linear phase, already we have seen, no? Linear phase means what? Distortionless transmission. See, theta of omega is equal to omega, or theta of F is equal to F. So, group delay phase delay so group delays phase delay are equal and it is equal to constant. For a distortionless transmission, remember linear phase channel means distortionless transmission, phase delay and group delay are equal and it is equal to a constant. It is equal to a constant. Right. So, this is regarding the distortionless transmission. Tomorrow I will start Hilbert transform. I request all the electrical students also attend the Hilbert transform because you will enjoy like anything. It is just an application of Fourier transform, small application. After that we will start tomorrow only Laplace transform. So, these are our channels. So, propagate the information regarding these channels to your friends. You can follow me on Unacademy, unacademy.com @KV Swamy. And finally, thank you. Tomorrow, what is the agenda? One previous gate question for group delay and phase delay first. After that, Hilbert transform. And if you want to have strong foundation of Hilbert transform, go through the Fourier transforms, concepts of Fourier transforms and come. After that, I'll start Laplace transform. Okay. Stay safe, stay healthy, take care. Thank you.